Hello, this is a demo video of our team to build the artificial neural network to laboratory, and I will introduce the work about part 1. And in part 1, we need to build up a AN value network first, and this is a formula, and here is the profile which we do, and this part is how we define the value network here, as the tutorial says. And in second part, we need to build a 2-layer MLP and SDG. And you can see here what we work as the tutorial says. We have a forward function, we have loose function, and backward and step. This is the parameter for our model. And as the next part, you have a bench layer and train function, which is used to define the parameter which we use to train our model. And as you can see here, we have epochs of 200, which we can change here, and layer, the learning rate, and the bench size with decay. We don't need to decay here, and yeah, that's how we define the training function. And as the last part, in the main function, we have 3 applications. The first application is about 1D linear regression, and the second one is a two classes classification, and yeah, the third one is about a multiple multiple classes classification, and here we do the 3 blobs, and we can output the result, and we can see the training accuracy and the looks function in every purchase. And that's all. We built this by Python and NumPy, and finally we run this function and have a very good result, which I will show you here. For the first application, we have a retraining for 500 epochs, which linear rate of 0.01, and as showing off the results, the loss decrease steadily from like here to decrease at very low level, which means our model is successfully convergency. And after training, we evaluate the model on the set of inputs, and the predictable is like here is the x, and here's the y, and this is our how we predictable. So here is how we predict our linear function, and here's the data size, and it shows our linear relationship is very good. And in second application, we're doing binary classification, and the model is training for 200 epochs in a linear rate of 0.005, and in the result shows we have a decreased looks function value, and finally we have a training accuracy about like 99%, which very closely to fully success predict, and which shows that our model is very efficiency on the 2 classification. And in the third part, here's the result. We're also training for 200 epochs, and with a linear rate same to the 2 classification. And as the result shows, the loss decrease steadily. The loss function keep declosing here, and finally we have after the training, we have a training accuracy about like 95% percentage, which is a very high level of the successful predict our classification. So I think our model predict very well on 3 application, and it's very successful in this part. Okay, that's all.
Hi, this is Wenxiao. In this demo video, I'm going to show how to implement a simple CAN using only NumPy to train on the Kaggle dogs versus cats dataset. First, we log into the Kaggle account and create API to get everything ready for downloading data. This is a screenshot. And then we enter the website link. This is the website link. We enter this link to join the computation of the dataset. This is the join, and after that, we install Kaggle and download the dataset onto our PC. Because the original dataset doesn't separate the cat and dog pictures, so we did it manually. This is the dataset. We separated the cat and dog pictures. This is cat pictures, and this is dog pictures. And this is the code. The load data function reads each image and converts it to the RGB, resizes it to 64 by 64 pixels. 64 by 64 pixels, and normalizes it to a closed interval 0 to 1. Next, helper functions: RELU, derivative, MSE loss, and gradient. Then we initialize a 3 by 3 by 3 convolution filter and a fully connected layer with small random weights. Each image passes through a 3 by 3 convolution. RELU activation, 2 by 2 max polling, and a fully connected layer. We set the learning rate to 0.001 and train for 10 epochs. In each epoch, we forward the image, compute MSE loss, then backpropagate and update weights. After training, we evaluate the model on unseen 20% of images. We also measure the total testing time, average milliseconds per image, and throughput, which is images per second. And these are the results. As you can see, the model learns to distinguish cats and dogs to some extent. Accuracy and speed depend on dataset size and epochs. The total training time is 2594 seconds, and on the test set, the accuracy reaches about 49%, which is only slightly better than random guessing. And for inference, processing 5,000 unseen images took 45 seconds. Averaging time is about 13 milliseconds per image, with the throughput of 76 images per second. This result demonstrates that our NumPy CNN works correctly, but it's very slow because all computations run on the CPU.
Okay, in part 3, it's a simple convolutional neural network for cat versus dog image classification. It's a PyTorch GPU version of the Part 2 model, which is originally implemented with NumPy. you can see the dataset is organized in image folder with separated folders, cats and dogs. Each image is resized to 64 by 64 pixels before training. The network has two convolutional layers with a rule activation and max powering, followed by two fully connected layers. The structure is simple but effective for binary image classification, and also we use add-in optimizer, and with a learning rate of 0.001. The loss function is MSE with a binary target of 0 or 1. And the entire training process runs on the GPU. As you can see, the result shows we're using device CUDA. And also the code can automatically save the best checkpoint during training, like this. After training, we test the model on a small folder of unseen images, and the program prints out the predicted labels, showing whether the model thinks it's a cat or dog. And you can see the results. With the processing, we can see the accuracy can reach about 80%, which is much higher than the NumPy version, and the total training time is 700 seconds, while in NumPy version it may be several thousand seconds. So in summary, this PyTorch GPU version is more effective and achieves higher accuracy than the NumPy implementation.